Hello to everyone. I am Dr. Alkesh Agrawal, and in this lecture, I'll mainly discuss about the design process of half adder and full adder combinational logic circuits. But before that, we'll discuss about the XOR gate and the AND logic gate, because these two gates are being used in order to design a half adder combinational logic and a full adder combinational logic circuit. These are some reference books. One is Digital Design, authored by Morris Mano and M.D. Saletti, and another book is Modern Digital Electronics, authored by R.P. Jain. So, before discussing about the design process of half adder and full adder, let us discuss about the gates that are being used in order to design a half adder and a full adder. The one is exclusive OR gate. This is the gate diagram of an exclusive OR gate. This is a two input XOR gate, and this is the Boolean function. Output Y is being related as with inputs as A and B bar or A bar and B. This is the truth table of exclusive OR gate, and the importance of this exclusive OR gate is when the inputs are of opposite nature, we get high output, and when the inputs are of same nature, we get a low output. So here you can see for 0 0 output is low, for 1 1 input we have output is low, and when for 0 1 and 1 0 we have output is high. So you is already being written here as a note that an XOR gate output is 1 when the inputs are of opposite nature, that is 0 and 1 or 1 and 0, and XOR gate output is 0 when the inputs are of same nature. Then we have an AND gate. This is the gate diagram. This is a two input AND gate. This is the truth table of AND gate, which clearly shows that when all inputs are high, we get a high output. In rest all other conditions, we get a low output. This is the Boolean expression y is equal to A and B. So an AND gate output is high when all the inputs are high. So now let us discuss about the design process of a half adder. Here in general, a design process is being described. The first step is, from the specification of the circuit, we have to determine the required number of inputs and outputs, and then we have to assign symbol to each input and output. So we have a half adder. We know that a half adder is a combinational circuit which is capable of adding two input bits. So here we have two input bits. It generates two outputs. One is sum and one is carry. So the requirement is of two inputs and it generates two outputs. So we designate input 1 as A, second input as B, and one of the output is designated as sum, another output is being designated as carry. So first we'll discuss how it works. So before that, the second step is we derive a truth table that defines the required relationship between inputs and outputs. So inputs are A and B and the outputs are sum and carry, and we have this truth table. So before going into the details of this truth table, we have to discuss these rules, how this full half adder adds. So if input bits are 0 and 0, the sum is 0 and carry is 0. If input A is 0 and input B is 1, so when we add 0 and 1, it generates sum 1 and carry will be 0. If input, the reverse condition, input A is 1 and input B is 0, again sum generated is 1 and there is no carry generated, or it is being propagated to the next stage. If both inputs are 1, so here in this case sum is 0 but a carry is generated and it is being propagated to the next stage. So you have to see over here is the sum is confined to the same stage and carry is being propagated to the next stage. So based on these rules, we have the sum and carry. So when 0 added to 0, sum is 0, carry is 0. When 0 is added to 1, sum is 1, and there is no carry is generated for the next stage. When 1 is added to 0, the sum is generated in that stage and no carry is being generated and propagated to the next stage. When 1 is 1 added, we have a sum 0 in that stage and a carry is generated and propagated onto the next stage. So we have sum as 0 1 1 0 and carry as 0 0 0 1. Now, if we correlate these two outputs with the two gates that we described early slides, we see that the output sum is matched with the output of XOR gate, and the output carry is being matched with the output of a AND gate. So here the third is, now we have to obtain a simplified Boolean function for each output as a function of input variables. So sum AB is, here for sum we have output 1 and 1 for combination A bar and B, and this output sum is 1 for combination A and B bar. So we wrote as sum as a function of AB as A dash A bar and B, or A and B bar, from this truth table. And for carry A and B, we have only one output as high when A is 1 and B is 1. So we wrote carry A as a function of A, B is A and B. So in order to realize sum, what we needed is a 2-input XOR gate. We can see through this expression, and for implementing carry as A and B, we need a 2-input AND gate. So now we'll design. The last step is to draw the logic diagram and verify the correctness of the design. So here we have two inputs A and B, and the sum is being generated through an exclusive OR gate. So the input A and input B are connected to the exclusive inputs of exclusive OR gate, and you can see the same inputs are being connected to the two inputs of the AND gate. So with the same inputs, we are getting two outputs. Output sum as exclusive OR values of inputs A and B, and output carry as an AND value of A and B. So this is how we realize a half adder with the help of two gates. First is exclusive OR gate, another one is the AND gate. Now we'll move on to a full adder. Now full adder is has three inputs and two outputs. Now the third input is the carry that is being propagated from the previous stage, that I'll discuss later on. So it has three inputs, A, B and C in. What is C in is the carry in, which is being propagated from the previous stage, and then we have two outputs, sum and carry. So the basic rules for addition are the same as I described previously. Now here, since this full adder adds 3 bits, so here you can see if we have all the bits as 1, input A is 1, input B is 1 and C in is 1. So in this case the sum is 1, which is fixed in this stage, and a carry generated is 1, which is being propagated onto the next stage. Now let us see this example. Here I have shown addition process in 2 stages. In the one stage, the carry that is being propagated from the previous stage is 0, because this is the first stage only and this is the second stage of addition. So in the first stage, no carry is being propagated from the previous stage, and input A is 1, input B is 1. So when we add these 3 bits, sum is 0, sum is 0 and carry is 1. So sum in this first stage, S1 is 0 and carry generated is C1 is 1, which is being propagated onto the second stage. You can see this is the carry that is being generated in the first stage and propagated onto the second stage. Now we have C in as 1, the C in is 1, and then A bit is 1, B bit is 1. So because of this, we need a full adder. Here we can add these 2 bits with half adder because C in is 0, but in order to add 3 bits, we need a full adder where 1 bit is the carry that is being propagated from the previous stage. So we have carry propagated from the previous stage. We have bit A as 1, bit B is 1. So when we add these three ones, we get sum, second stage sum as 1, and the final carry out is 1. So when we add, what we get final is 1, 1 and 0. So this is how a full adder works. Now let us discuss with this truth table. So we have three inputs A, B and C in. Since these are 3 bits, so we have 8 combinations from 0, 0, 0 to 1, 1, 1. So how we understand this? We take two conditions when the carry input is 0 and when carry input is 1 for input bits 0, 0. Then for input bits 0 and 1 we have carry in 0 and carry in 1. That is one case when there is no carry that is being generated and propagated on to the next stage, and this is the case when carry is being propagated from the previous stage. Again, for input bits 1, 0 we have C in as 0, and for 1, 0 bit we have C in as 1. So again, two conditions with the same input combination 1, 0, and then if the input bits are 1, 1 we have one case when carry is not propagated from the previous stage, and another case is when carry is propagating from the previous stage. So with all these combinations, when all the bits are 0 we have sum 0 carry 0. When we add 0 0 1 we have sum 1 and carry 0. When again we add 0 1 0 we have carry sum 1 carry 0. When we have addition of 0 1 1, in this case you know by the rule sum is 0 and carry is 1, final carry is 1. If we add 1 0 0 sum is 1 carry is 0, again 1, addition of 1 0 1 we have sum 0 and carry 1. With this combination of 1 1 0, addition of 1 1 and 0 we have sum 0 and carry 1, and with all the bits 1 we have sum 1 and carry 1. So here this we can see that in this truth table the sum output we have in 4 conditions we get high value, that is for if for minterm 1, minterm 2, minterm 4 and minterm 7 we get a high value. So this Boolean expression from this table comes out to be sum as a function of A, B, C in is summation M 1, 2, 4, 7 from the truth table. And for carry we have again output for M3, M5, M6 and M7. So we get carry output as A, B, C in as summation M3, 5, 6, 7. So now by these two Boolean function, now we will be able to design a full adder, which are very important. So these two Boolean functions are being generated from this truth table. Now let us see the 3 variable k map. So we plotted a 3 variable k map for calculating the expression of sum. So we have m1, m2, m4, m7, and we know that in the previous lecture I discussed that this is a special case where none of the minterms can combine with the other. So in this case the final expression comes out to be the exclusive or value of all the input variables A exclusive or B exclusive or C in. And now for calculation of carry output we have carry as a function of ABC in with minterm value 3, 5, 6 and 7. Now here we have 3 groups, combination of 2 minterms at a time. So we have one group of M3, M7, another group of M5, M7, another group of M7 and M6. So from this group when we reduce we get B and C in. From this group we get A and C in, and from this group we get A and B. So what we get is a very simple expression as A and B or B and C in or A and C in. So you can see we have a combination of 2 inputs, so A and B or B and C in or A and C in. Now the same K-map can be reduced in this form where we have combination of M7, M6 and one group, and we took isolated ones. This is because we can show that a full adder is a combination of 2 half adders. So we know that all the minterms are the same except the kind that the process by which we are reducing the minterms. So here we are taking M6 and M7 in a group. So by that we get a reduced value of AB. For this isolated we are taking this as isolated one, so we get A bar and B and C in because A is 0 and B and C in 1 1, so we get A bar dot B dot C, and for this isolated one we get is A is 1, so we get A, and B and C 0 1, so we get B bar and C. If we combine these two values, so we get C input as common, so we get A and B bar or A bar and B. So this whole value comes out to be A exclusive or B and with C in or AB. So this expression is very useful when we generate a full adder with the help of two half adders. Now here we can see this. So we have, now this is the gist of a full adder. So we have these two Boolean functions, sum as a function of AB seen as summation m1 2 4 7. Then we have a carry AB seen as a summation m3 5 6 7. We get an expression sum as exclusive or value of A, exclusive or B, exclusive or C in, and carry we get two expression A and B or B and C in or A and C in, and this is another expression we got for the same as A exclusive or B and C in or A and B. So now we know that a half, we have shown that a full adder is a combination of two half adders. So here we have shown this is one half adder, this is another half adder. Now the for you know that a half adder takes only two inputs. So in the first half adder we have input A and input B, and in another half adder we have input A as the output of first half adder, and another input is C in. So in both the half adders we have two inputs. Now we'll explain how it works. So this output is A exclusive or B, which is input to the next half adder. So and another input is C in. So final expression of sum what we get is A exclusive or B exclusive or with C in. So this is the sum. Now here you can see, if you look into this expression, so this is OR value of A and B. A and B is carry from this stage, and A exclusive or B and C in is the carry from the second stage. So the final carry can be generated from the first half adder or from the second half adder or from the both. So we have odd value of carry from the first half adder, from the second half adder, or from the both. So from first half adder we have A and B. From the second half adder we have this input is A exclusive or B, this is C in. So what we get is A exclusive or B and C in, was ANDed. So final value is odd. So what we get, this value is A exclusive or B and C in, and this is odd with A and B. So final expression of carry what we get is A exclusive or B and C in or AB, because this is the carry from the first half adder, this is the carry value of the second half adder. And like this, a full adder is a combination of two half adders with sum as A exclusive or B exclusive or C in, and carry as A exclusive or B and C in or AB. So this is, we have shown that a half adder, full adder is a combination of two half adders. Thank you.